All right, textbooks open to page 116. You did numbers 16, 18, and 20, just 3 problems for homework over the weekend. And all 3 of them working with rational equations, proportions, if you will, so all of them needed to cross multiply. There were some shortcuts that we had talked about in a previous lesson, so curious to see how we did perhaps using those shortcuts in these problems. Number 16, though, there were no shortcuts. We just had to cross multiply straight up. When you multiplied the means, what did you get, Kendall?
8x plus 8.
Well, that's the extremes, but I guess we'll go with that. What did you get when you multiplied the means?
12x plus 30.
There we go. And we'll just set the product of the means equal to the product of the extremes. From there, we need to solve, Michael, by
moving the 8x over
to get
4x,
and then also move the
30 over
to get,
negative 22,
and it's not pretty, but when we divide by 4 and reduce, we end up with what answer, anyone?
negative 11 halves.
Negative 11 halves. There was no restriction on what x could be because the denominators would not equal 0 anyway. So our single answer is indeed an acceptable root. How many got this for number 16? Then on number 18, there was a little something we could do. We have a y positive 1 over y negative 7 equal to y squared positive 7y positive 6 all over a y squared negative 5y negative 14. What should we probably do first to make ourselves not have to do quite so much work, Genesis?
Factor.
I would factor first and just see if there's something we can do, maybe some canceling we could do here to simplify our life. How did you factor your numerator?
y plus 1 and y plus 6.
And in the denominator?
Y plus 2, y minus 7.
Now, ideally, we'd like to reduce just straight up and down within the same fractions. Obviously, nothing does reduce. I told you in the last lesson, you can cancel side by side only in the class denominator, because these denominators wouldn't be able to equal 0 anyway. So we could cancel away the y negative 7s. I said do not cancel the y positive 1s. Do not cancel numerators with each other. How many factored like Genesis did and canceled the y negative 7s? Did anyone fall into the trap of canceling the y positive 1s? If so, we had a challenging time with this equation. All right, so at this point, we've just got a 1 left here, and when we cross multiply the extremes here, we have to FOIL the binomials to get what, Maddie?
Y squared 3y positive 3.
And then when we multiply here, of course, since the 1's all that we've got here, that's going to leave us with both of these, and we can already see what that multiplies to, the y squared positive 7y positive 6 we factored in the first place. At this point, Audrey, we can cancel away the...
Y squared.
And again, if you cancel the y plus 1s, you would have lost those, and now you're left with y plus 2 equals y plus 6. The y's cancel, you get 6 plus 2. That's a contradiction. That just doesn't work. But instead, after we cancel the y squares, we should have done what, Abby?
Move the 7y over as a negative 4y.
Okay. And so we move the 7y over as a negative, get negative 4y, and then of course we'll also move the 2 over as a negative 2 to get
Positive 4.
positive 4. Again, it doesn't really matter. We can divide by negative 4 just as well as we can divide by 4. We're smart. We get...
Negative 1.
And that was not one of the things y couldn't be. Y couldn't be a 7. In fact, we canceled those away anyway. Y also couldn't be a negative 2. Why is it? It's a negative 1. If you didn't cancel these and you did the double distribution on both, you would have also gotten 7 for a root. You would have had to say it was extraneous. How many got negative 1? Did anyone do the double distribution? You got the 7 as extraneous and canceled it away that way? Any questions on number 18? All right, number 20, similar approach I would think here. We've got a 3x plus 1 over 3x squared negative x negative 4 all over x over 3x squared positive x negative 2. Brandon, off the top of my head, I'm not seeing the factors, but surely they do factor. Did you attempt to factor? And what factorest thou?
3x negative 1 and x positive. And 3x negative 2.
Yes. Sorry, I was just fact checking.
3x negative 2 and x positive.
Yes. All right. And what now?
cancel x positive ones.
Good. We can cancel the x positive ones because they're denominators. They would both end up being set unequal to 0 anyway, so you would get an x equals -1 if you didn't cancel them, but you'd already have to say it was extraneous. So let's just get rid of them right off the bat. When we then multiply the means, Kendall, what do we get?
3x squared -4.
And when we cross multiply the extremes, what do we get, Michael?
You get, let me find my answer. 9x squared positive 9x negative 2.
I can get a positive 9x. My outer's a -6, but the inner's a positive 3. -6, positive 3.
Negative 3.
There we go, -3x. And then you said what at the end?
Negative 2.
-2 is correct. This time my squares don't cancel, Genesis, so I'm going to end up with a complete quadratic equation, right? And so we want to set it equal to 0. Which side, the left or the right?
Left.
I'd make the left side of 0. Good. Let's bring the 3x squared over as a, to get
6x squared.
let's also bring the 4x over as a, to get,
1x.
and then of course we still have this -2. I think we can factor this. Let's give it a try, Genesis. How probably should we split up a 6x squared?
2x.
Probably 2 and 3, right? Maybe 6 and 1, but probably 2 and 3. Negative side, of course.
Different ones.
And then the 2.
1 and 2.
And if we check our outer inner, does that work? Yeah, so I end up with 2 answers for x. X could be, Maddie,
Negative,
positive 1/2, or it could be.
-2/3.
Now, are either of these answers off limits based on these denominators, class? No. Positive 4/3 is out and positive 2/3 is out, but I've got 1/2 working out and I've got negative 2/3 working out as well, and that is what the book has also. How many had those same answers? All right, questions on this? If we didn't get it, did we find our mistake as we went along? All right, questions, comments? All right, let's go and take a look at some word problems together now. And we began looking a couple lessons ago at word problems that have maybe a couple unknowns, but a couple different scenarios, such that I recommend using a table to keep track of everything, or a chart to kind of keep track of everything. This is going to be one of those problems. Read it for us if you would, Audrey.
James is 5 years older than his brother Joe. 2 years ago, he was twice as old as Joe. How old is each now?
How many unknowns?
2.
They are
Jim and Joe.
who? Jim and
Joe.
Joe?
Mm-hmm.
Who gets to be X?
Joe.
Joe, and how would we represent Jim?
X plus 5.
Good, because right now, and you're doing this with me there at your seats, Jim is 5 years older than Jim. Any questions so far? And all this really straightforward. But then, like we saw in the last problem, we're going to time travel. Except this time, I think in the last problem we saw something like this. We went into the future. Here, we're going to go back into the past. We've got this transitional phrase right here, 2 years ago. And Brandon, what's true of everyone 2 years ago? Good. All of us were 2 years younger, right? And it was pre-COVID, right? It was coming. We just didn't know it, okay? Can you imagine if we had known 2 years ago what we know today? If we'd known what was coming and how annoying that everything was going to be? Anyway, but we didn't know. Okay, so 2 years ago, everybody 2 years younger. So we're going to travel back in time, back into the past. How would I show Joe's age 2 years ago, Abby?
X minus 2.
X minus 2, right? Just subtract 2. How would we show Jim's age 2 years ago?
X plus 3.
There we go. And once we've represented the time travel, these are now their new ages as far as the problem is concerned, because now we come to the equation. He was twice as old as Joe. Who's the he here, Kendall?
Jim.
It's got to be Jim, because it can't be that Joe is twice as old as Joe. I mean, other than the moment he's born, you're never twice as old as yourself. 2 times 0, of course, is 0. But yeah, he was twice as old as Joe. He must be Jim. So how would I represent Jim as I get ready to write the equation? That's old news. We've moved past that. That was so last sentence. X plus 3. Right. Now that we're in this new sentence, we've traveled back into the past. So this is now Jim. This is 2 years ago, Jim. And he says was, class, was equals. Right? That's our linking verb. That's our equal sign. It says twice as old as Joe. How would I show twice as old as Joe, Genesis? Well, is Joe, but again, that's so last sentence. Let's keep up with the times.
2x minus,
Okay.
2x minus 4.
There we go. Hey, we're in Algebra 2. We can distribute, right? We can do that all in our head. Yeah, twice this Joe, right? The 2 years ago Joe. So the 2 years ago he, or the 2 years ago Jim, was twice as old as the 2 years ago Joe, because we've traveled 2 years ago. Questions on that? How many remember this from the last lesson, or I guess 2 lessons ago when we last looked at this? All right, then to solve, really straightforward, just pull a double switch, right? Send the x over as a negative to just get x, and 4 over as a positive to get. And very easily we see that Joe is now 7, and Jim is 12. But if you go back 2 years, Jim would have been 10. And Joe would have been, and sure enough, 2 years ago, Jim was twice as old as Joe. But it says how old is each now, so instead of 10 and 5, we'll go with 12 and 7. Questions on that? All right. Let's take a look at another problem that's somewhat similar to a problem that we did last time. I think we looked at Granny Smith, or Mrs. Smith, or whoever it was. Anyway, I don't know if that was foreshadowing, but my wife ended up buying a Mrs. Smith pumpkin pie for Thanksgiving. I don't know. Anyway, I didn't tell her to. But Mrs. Smith and the apples. Well, anyway, this time it's a teacher of unknown identity who buys donuts for his math class, because some teachers are cool like that. Anyway, go ahead and read this for us if you would. Let's see, you read the last one. It's not 10 donuts. Go ahead, Maddie.
This is about one donut for each student in his math class. About 3 more regular glazed than filled. Filled donuts cost 80 cents each, and the regular glazed cost 60 cents each. If he spent $13, how many students are in his class?
All right, so how many different unknowns do we have here? It's kind of a weird twist at the end, but how many unknowns are we really looking at here, Michael?
2.
2, and they are
Regular and filled.
right. We're not so much. It ultimately wants to know how many students are in the class, right? But by finding that, we're finding how many students got a filled donut and how many got a regular donut. How many like just plain old regular glazed? Don't give me anything extra. I just like normal donut. How many like if you have a choice, if you're going to spend the money on a donut, you're going to do something like cream or jelly or something like that. Anyway, I had this. Somebody brought Krispy Kreme donuts for Sunday school, and I had an apple pie Krispy Kreme donut. It had like a little bit of caramel on the top with the streusel topping and the apple pie filling in the middle. Oh, it was delicious. Maddie's like, I don't eat donuts, so I don't care. All right. Anyway, so I had a class one year, though, a senior class, who decided to do a senior prank on me, and I decided that I was going to repay their evil with kindness. And so when they got back from their senior trip, instead of berating them or punishing them, I got them all donuts, and I got them filled donuts. I'll leave the story there. Anyway. So 2 unknowns, and you said they're what, Michael?
Regular and filled.
Regular and filled. And you could argue students who got regular and students who got filled, but whatever. Which one gets to be X here, Michael?
Filled.
Right, you got 3 more regular glazed than filled, so filled will be X, and we should represent regular class.
Plus 3.
X plus 3, because there were 3 more of the regular glazed than there were filled. Now this refers to the number of regular donuts that were bought, or the students who got regular donuts, and then the number of students who got the filled donuts, right? But there's something else about the regular and filled that's different. Not just are the number of regular and filled different, and these prices are pre-Biden inflation numbers, And the value, or how much it costs to get each. This is a very old word problem, actually. Like this is even pre-Trump. So for those of you Trump supporters, he can't take credit for those prices either. That goes back to like Obama administration. Because inflation did continue to rise under Trump, just not nearly as much as it's been in the last year. But anyway, I digress. This isn't a political class or government class. Each regular donut class, according to the problem, costs 60 cents. Now, later on, it's going to switch to dollars. And here it's cents. So I should probably write my 60 cents as a dollar amount. What would that be, class? $0.6, right? Would be 60 cents or 0.60, but I'm too lazy to write the 0. And then the filled donuts cost 0.8, 80 cents each, right? Now, of course, if there had been only, let's say, one filled donut, and all the filled donuts cost 80 cents, how much money was spent just on the filled donuts?
80 cents.
80 cents. What about 2 filled donuts?
$1.60.
$1.60. What about 5 filled donuts?
4 cents.
$4, right? $4. All we do is figure out the total money spent on each one of these is we would do what, class? Multiply the number of each times the price of each to get the total money spent on each kind, right? So the money spent on filled donuts, class, was 0.8x. And the total money spent on regular donuts must have been
0.6x plus 18x.
There you go, 0.6 times x plus 3. Or if you want to distribute, you said 0.6x plus
1.8x.
1.8. Oh, careful, not 1.8x, just 1.8, right? And that's if you want to go and do the distributed form. Make sense? There's one number we haven't used yet. Of course, that number, Brandon, is the $13. This must be a really nice math teacher. Spend that much money on donuts. But anyway, what's the? I didn't spend that much. What's the equation going to be, Brandon?
0.6x plus 1.8 plus 0.8x equals 13.
There we go. Take the money spent on the regular donuts plus the money spent on the filled donuts equals all the money that was spent total. Make sense? So the last column, if you simply add it together, that'll equal the grand total. How many remember doing the similar problem with the apples, the Red Delicious and Gold Delicious apples? Questions on this? Represent the number of each. Often that's where the unknown is, though we will work some problems moving forward where the unknown will be the value instead. Represent the value of each. Again, if the unknown is in the value column, usually the number of each would be known. Multiply to get total money, and then money plus money equals money. Right, Maddie? And so we take all this money plus all this money equals that money. And I don't really like all these decimals. That's just really annoying. So Genesis, let's move them to get what new equation?
6x plus 18 plus 80.
Sorry, there is a decimal there.
Oh, 8x equals 1/3.
There we go. There wasn't a decimal there. So that's how we did have to annex the 0 or add that on. We combine our x's, class, to get 14x. And let's at the same time, let's ditch the 18 as a negative 18 to get 112. And we end up with what when we divide by 14? Calculators are available.
8.
And you knew it had to be an integer, right? Because nobody is selling a 2/3 donut, right? Or something weird like that. I got 8.7 donuts. Where did the 0.7 come from? You know, not from siblings. Siblings 8.3 of one of the donuts. But this is how you bought the donuts. So we assume that the donuts are whole. So we're excited to get an integer value here, which means there were 8 filled donuts that he bought, and how many regular? 11. But the question asked, how many students are in the class? 19. 11 plus 8. Unless, of course, you say, well, the teacher ate one himself. But it doesn't say the teacher ate one himself. So we can assume 19 students in the class. Questions on this type of word problem? Probably make sure. Oh, yeah, just barely fit on the screen. Good. All right, questions on this? All right. Next section in your notes. We'll continue working on word problems like these in the days ahead. For now, next section in your notes, we've been talking about all different kinds of equations. We're going to move on to a new type of equation, radical equations. Next section in your notes, radical equations. Radical equations would be equations with radicals in them. You don't have to write that down. We just need to know, how do we go about solving these radical equations? Step number one is solving a radical equation. For instance, something like the square root of x minus 3 is equal to 7. It's a really basic, easy radical equation. The radical kind of makes things messy, right? But the radical is very attached to the x, isn't it? So we can't easily get rid of that radical. We've got to, just as if there were a 2x, we'd say, well, let's get rid of the 3 before we get rid of the 2. So here, we want to get rid of everything but the radical first. So step number one is to isolate the biggest radical. Isolate the biggest radical. Now, I phrase it this way because we will work problems that will have more than one radical later. Obviously, if there's only one radical, it are the biggest. All right, so isolate the biggest radical. That would be the square root of x, because that's the biggest radical. All right, isolate the biggest radical. Again, the biggest is really there because if we had more than one, you'd want to isolate the ugliest one. Step number two is to square both sides. But I want you to put an asterisk after the word square. And I want you to underline the word sides. A lot of times in algebra, we can get away with doing something to everything. Multiply everything by 2, or divide 2 out of everything. Well, when it comes to squaring, you can't square everything. You have to square both sides. The reason for the asterisk, if this were a cube root, I wouldn't square everything, or square both sides, rather. I would cube both sides. If it were a fifth root, I would raise both sides to the fifth power. Does that make sense? Because you want to get rid of the radical. So, for instance, here, to isolate the radical class, all I'd have to do is put a positive 3, or move it over as a positive 3, right? To get the square root of x is equal to 10. And remember, we always do the opposite in math, right? So to get rid of a radical, since it's a square root, the opposite of a square root is to square. So we square both sides, just like when we were completing the square. To get rid of the square, we took the square root. To get rid of the square root, we square. Make sense? We're doing the opposite. And the square root cancel, because when you square a square root, you get the radicand. Right? That was weak. I only heard him say it. When you square a square root, class, you get the radicand. So that gives me x is equal to 100. Now, if there were more than one radical, you would isolate the biggest radical, square both sides, but you'd still have another radical present. So the third step would be to repeat 1 and 2 if necessary. If you have multiple radicals, you'd have to repeat those steps until all the radicals are gone. So in some cases, you have to go through it again. Here we didn't have to. Step number 4 would be simply to solve. And in this case, the solving's already done. We've already got x is equal to 100. But I want you to put a star next to this, because this will come up from time to time that you may not make any mistakes in the working of the problem, and yet your answer doesn't check, or one of your answers may not check. So check for extraneous roots. Check for extraneous roots. A couple of key times. 2 key times you're going to see extraneous roots. If you have multiple radicals, this is very common to get an extraneous root. The other time it's common to get an extraneous root is if you have multiple answers or multiple roots to begin with. So if you have multiple roots, it's very possible that one of them or more may be extraneous. Or if there's multiple radicals in a problem, and we'll see that hopefully later on this hour, it's possible you may only get one answer and it may be extraneous. You may have no solution at all. So there's a couple times where it's really important to check. Here, we don't have multiple radicals. I don't have multiple roots. Probably don't need to check. But if you wanted to, what's the square root of 100, class? 10 minus 3? We're done. All right, so it checks. But again, single radical or single root answers, really not as big a need to check. Write this down if you would. 2 times the square root of x plus 1 minus 1 is equal to 5. This is an equation because, class, it has
Equal sign.
An equal sign. It's a radical equation because not only does it have an equal sign, it also has a radical. Therefore, I call it a radical equation. And my first step to solving a radical equation, class, is to isolate the radical. Biggest radical, but in this case there's only one. So isolate the radical. Two things I have to do to isolate the radical. First, Brandon, add the 1 to the 5 to get 6. I'm going to do the lazy way. And then I also need to get. Alright, now the radical is isolated. We have the square root of x plus 1 equals 3. Go ahead. I went ahead and rewrote it just so it looks a little clearer. You don't necessarily have to. Now that the radical is isolated, step number 2. Class, square both sides. It's on the chalkboard. It's in your notes. You just read it. Square both sides. When you square a square root, you get the radicand. So when I square the square root of x plus 1, Abby, I get?
X plus 1.
When I square the 3, class, I get 9. Do I need to repeat? No, there's no radicals left. So I go to step 4, which is solve, which is one easy step here. All I need to do now, Audrey, is to, and that's going to give me x is equal to 8. I don't have multiple answers. I did not start with multiple radicals. I probably don't need to check, but it wouldn't hurt to check either. What is 8 plus 1, class? Square root of 9 times 2 minus 1. There we go. It checks out. Questions? Write this one down. 4 plus the cube root of 2x is equal to 10. 4 plus the cube root of 2x is equal to 10. In a radical equation, step number 1, class, is to isolate the radical. In this case, there's only one, so I don't necessarily need to isolate the biggest. Put that in brackets in case I need it later. But isolate the radical, right? And one easy step to isolate the radical here, Genesis. I don't have a square root of a negative, so I didn't pull out an I. To isolate the radical, what's with the radical right now?
The square root.
Well, that is the radical, right? So this right here is the radical. How do I isolate it? How do I get it by itself? What's with it right now? Okay, this whole thing is considered the radical, okay? So there's the equal sign. Going back, to really basic equation. Equal sign's like the wall.
Divide away the... No.
The 4, right? The 4 is with the radical. But the 4 is a separate term. It's not being multiplied. So to get rid of the 4, I need to move it over as a negative 4. Does that make sense?
Yeah.
All right, it's Monday, all right. So we got the cube root of a 2x, all equal to 6. Normally, my 2 steps, class, are isolate the radical, square both sides. Isolate the radical, square both sides. But this time, tricky. Isolate the radical, cube both sides. How many? Yeah. All right, so we need to cube both sides. And when I cube a cube root, I get the... Hey, I never even taught you that. You figured it out. Good. And that just gives me 2x. And cube of 6.
260.
How many did it without the calculator? Good job, Michael. He's like, I didn't use a calculator, just listen to them. All right. And then to finish solving for the x, class, we need to divide away the 2. So we now need to do step 4, solve. Divide away the 2 to get x equals 108. And we do that without the calculator? All right. And so there's my answer. If we wanted to, we could check. We could plug in the 108. 2 times 108, class?
216.
Cube root of 216? 4 plus 6? 10. There we go. It checks out. Questions on that? Isolate the radicals, square both sides. Isolate the radicals, square both. It's what we do to solve radical equations. Except in this case, it was cube both sides. Write this one down. 3 times the square root of 3x minus 5 is equal to 7 plus the square root of 3x. Now here I have multiple radicals, but look at them. What do we notice about the 2 radicals in this problem, Kendall?
They're the same.
They're similar. Same index, same radicand. And if you have similar radicals, you can add them, though they're on opposite sides of the equal sign. So rather than combining them, I'm actually going to choose to get rid of one. And we always get rid of the... That's even true of similar radicals. I'm going to get rid of the little radical. Which one's little, Kendall? 3 square root of 3x or square root of 3x? So I'm going to get rid of this. I'm going to move it over, and it's going to become a...
Square root of 3x.
Good. Well, what do we get if we take a 3 squared of 3x and we subtract or put a negative square root of 3x, class? 2 times square root of 3x. 3 squared root of 3x minus 1 square root of 3x equals 2 squared root of 3x. Negative 5 is equal to 7. Make sense? You won't see this very often, admittedly, where you'll have similar radicals in the same problem. But if you did, I wanted you to see what it would look like. From here, we go back to our 2 main steps, class. We isolate the radical, square both sides. Let's try that again. Try to get everybody participating here on this Monday. Step 1, class.
Isolate the radical, square both sides.
There we go. The enthusiasm is lacking, but you know, what do you expect? So then what do we do, Michael?
You gotta isolate.
We do. So what do we do?
You take away the 5 and add 5 plus 7, which gives you 12. And then you divide away the 2, and that gives you 6.
All right, so we've isolated the radical. The square root of 3x is all equal to 6. Now that we've isolated the radical, Maddie. Oh no, Maddie. Once we isolate the radical, then we... There we go. Good, good. And by the way, you're going to need to be able to do this in higher math as well. So I'm going to those 2 steps to kind of just embed themselves in your brain. Isolate the radical, square both sides. So every time in higher math you see a square root equation or radical, isolate the radical, square both sides. So what do we do, Maddie? Because we already isolated the radical. And so when we square both sides, the other thing is when you square a square root, you get the radical. And that should be embedded in your brain too. So here I get... There we go. And then we just divide away to get x equals 12. And again, these multiple radicals, because they were similar, there might as well have just been the one. We don't necessarily have to check. If you did, it would work out. Questions on that one? How many feel like you're kind of getting the idea? Good. Good. Let me insult your intelligence a little more. Write this one down. The square root of 3x plus 4 is equal to 7. 2 steps for this radical equation, class. Isolate the radical, square both sides. This remind me of the Wednesday night song leader. You know, it's like everybody's tired. Let's sing as slow a song as we can. You know, it's like, come on, we need to pick something that's faster. Maybe sing. Anyway, isolate the radical, square both sides. Well, thoughts on step 1, class?
It's already isolated.
It's done did. It's isolated. So all we got to do is go to step 2, which is to square both sides, Audrey.
3x 4 equals 49.
And now finish it out here, Genesis.
-4. 45. 15.
And there we go. Questions on that? Seem pretty easy? As you see, so I want you to do page 115. Numbers 4, 6, and 8 at the top of the page. Page 115 at the top of the page, numbers 4, 6, and 8. Michael's finished, Abby's finished, Brandon's finished. Not necessarily in that order. Audrey's finished. right, let's go and take a look at these together. Number 4, frankly 4, 6, and 8 on all of them, I already isolated the radical for you. So, not to insult your intelligence or anything, all you had to do in each case to start out class was square both sides. And what did you get for your answer on number 4, Abby?
A equals 63.
Good. How about number 6, Brandon?
Y equals 148.
Yep. And then number 8, Maddie?
X equals 12.
Uh-oh, I thought we were insulting intelligence. Maybe not. Audrey? 14. Should have been our answer there. So real quick for YouTube, because I realized I didn't restate the answers. Number 4 was 63. Number 6, 148. Number 8 was 14. Did you find your own mistake, Maddie? All right. How many got all 3 correct? All 3 right. All right, questions. Maddie figured out what she did. Any questions, comments? See, I didn't get that answer. Which one?
For 6.
For 6. When you squared both sides, did you get y plus 21 equals 169?
No, I did y plus 13 equals 12.
Oh, all right.
I don't know.
Question on that.
Oh.
All right. It's Monday. All right. Get more sleep at night. All right, so those really straightforward. They can get a little bit more challenging, of course, if you were to have a problem like this. Write this down in your notes if you would. The square root of x plus 5 minus 5 equals x. But the process doesn't change. My first step, class, is still to isolate the radical. And here to isolate the radical, of course, we need to add the 5. But instead of a number being over here, where you just add the 5 to it, when you add the 5, you're going to have to leave the binomial x plus 5. Make sense? But the steps have not changed. The second step, class, is still to square both sides. And of course, you're still squaring a square root, so you still get the radicand, class. But on the other side, you're no longer squaring an integer, you're squaring a binomial. And that takes 3 steps. Square the first, square the last, multiply and double. So what do we get when we square the first? Square the last, multiply and double. Brandon?
X squared. 20. 50x.
Multiply and double.
Oh, 10x.
There we go. X squared positive 10x positive 25, our perfect square trinomial, right? Oh, and now what started as a radical equation, class, as we come down here to step 4, no more radicals to worry about, we do need to solve, right? I now suddenly have a complete quadratic equation where I'm going to need to set it equal to 0, move the x over, class, as a negative x, and the 5 over as a negative 5, and all right, that means we've got x squared plus 9x plus 20. And let's see if we can factor it, because I don't want to complete the square with an odd number. It looks like I should be able to factor it. Split up the x squared, class. Positive sign.
Positive.
Both signs the same. In this case, they are both positive. How to split up the 20?
4 and 5.
4 and 5. Okay. And I know I heard 5. It just sounded like a 9 somehow. My ears are really bothering me. All right, and then we set each of these equal to 0, and I get multiple roots. What are my 2 possible answers for x?
Negative 4 and negative 5.
Negative 4 and negative 5. I want to go back to the original problem. Remember, originally this was the square root of x plus 5 minus 5 equals x. Let's try plugging in these values. If I try a negative 4, negative 4 plus 5, class, 1. 1's square root is 1 minus 5, negative 4. Let's try negative 5. Negative 5 positive 5, 0. Square root of 0, 0 minus 5.
Negative 5.
In this case, no extraneous roots. They both work. But check when there's multiple roots. The multiple roots will usually come when there's a radical in and a radical out. You say, that sounds familiar. Right, absolute value equations did the same thing. When you had a radical in and a radical out, you had to be careful. Same thing here, or value in the absolute value out of the absolute value. Same thing. Well, here, variable in, variable out, especially good to check. Write this one down. 3x is equal to the square root of x plus 3 plus 1. What should we do first here, Kendall?
Isolate the square radical.
Isolate the radical by doing what?
Subtracting 1.
All right, to get?
3x minus 1 equals the square root of x plus 3.
And now that we've isolated the radical, Michael?
You got to square. Square.
Square what? Both sides. There we go. And again, not square everything, square both sides. So this entire side, this binomial must be squared, class. 3 steps, not 2.
Square the first, square the last, multiplying double.
And what do we get when we square the first, square the last, multiplying double? Genesis.
9x squared. 1. 3. 6. X. Negative.
There we go. And on the other side, we're just squaring a square root. We're just going to get
X plus 3.
the radicand, right? X plus 3. Once again, it turns into a quadratic. So class, I need to set it equal to
0.
0. This time, let's make the right-hand side the 0, Maddie.
No, it's going to
I think we can factor this one. That's a 0, not a 6. Let's give it a try, Audrey.
3x. Positive negative. 2 1.
Does that work?
No.
What if we flip the 1 and 2?
No.
No. Any other options on the factoring, or should we just go to the formula?
You can factor
9 and 1.
Abby's like, no, not the formula. I hate the formula. Couldn't help herself. 9 and 1. All right, let's try that now. Now outer inner. Yep. All right. So what are my 2 answers for x here, class?
Negative 2 ninths and 1.
Negative 2 ninths and 1. At least they're possible answers. But of course, we want to make sure that we check. Let's do the 1 first, because I'm lazy. All right. 1 plus 3.
4.
Square root of 4.
2.
2 plus 1.
3.
3. 3 times 1. 3.
Yay.
Calculator's ready. All right. Negative 2 ninths plus 3.
2 and 7 ninths.
Take the square root.
It gave me a decimal.
It did?
Yeah.
Plus 1.
Yeah, I'm at 2.
What?
2.67.
2 point what?
67.
2.67 or 2.66666667.
Yeah.
All right. On your calculator, 3 times negative 2 ninths. Negative 2 thirds, which is negative 0.66667, blah, blah, blah. Is that the same thing? No. So that means we have an extraneous root. Questions on this one? By the way, I will say the temptation, after seeing that, is, oh, I got it. If it comes out easy, it works. If it's weird, it doesn't. No. Sometimes the weird one will work and the normal one doesn't. Sometimes they both work. So you still got to check all of them, and that's why you're thankful you have a calculator. Let's do one more together, and then we'll be done. 3 times the square root of x minus x equals 2. Now here, I am going to deviate slightly from standard procedure. Because normally, class, my first step is to isolate the radical. But if I isolate the radical, we already know what that's going to do, right? We add the x, we divide by 3, and we get x plus 2 over 3. And then we have to square it, and we get this big, ugly, nasty thing. So here's what I'm going to suggest. There are times where it is advantageous for you to simply isolate the radical term. Here's one of those cases. where I'm going to move the x over as a positive, and now that the whole term is isolated, I'm going to go ahead and square both sides. Doing this with me. When you square the square root, you get the radicand, but you're not just squaring the square root, class, you're also squaring a 3. Square the 3 to get, and square the square root to get the radicand x. Does that make sense? To me, that's easier than meddling with fractions, because I hate fractions. Y'all with me? Y'all don't like fractions either? We like this better than dividing up the 3 down to a fraction? Okay. And on the other side, 3 steps, class. To get 4, positive 4x plus x squared. From here, I'll move the 9x over to get 0, setting it equal to 0. I'm going to flip it into descending order. X squared, negative 5x, when this comes over as a negative 9, positive 4. And this will factor pretty nicely. Anyone?
Negative 1, negative 4.
Yeah, x minus 1, x minus 4. So we get what two possible answers for x?
4 and 1.
Let's check the 4. Go back to the original. Square the 4 times 3 minus 4. Square root of 1 times 3 minus 1. And once again, we see an example where they both check. Doesn't always happen. Questions there. For homework this evening, I want you to do page 115. Practice 1 through 11, the teal. Page 115, practice 1 through 11, teal. So that is 6 different problems of these. 1 through 11, the teal. On page 115, have a wonderful rest of your day, and you are dismissed.